Hello and welcome back again. Finally, we've made it. La piste de résistance. In this module, we're going to be looking at resistance, capacitance, and inductance together and how they impact the circuit in both series, parallel, and in a combination circuit. So let's get to it. Hopefully by the end of this module, we'll be able to look at RLC circuits and how they impact both the power factors, the voltages, and the currents. We'll calculate all the values for voltage, currents, powers in RLC circuits. Let's start off by looking at series RLC relationships, shall we? A quick review of our series circuit's tenets is current is the same through any series set of components. The total opposition equals the sum of the individual oppositions together in series, and that turns out to be a vector sum in AC circuits. The applied voltage adds, and the total power of the individual powers add as well. Don't forget, in an AC circuit, everything is a vector sum. There's always an angle. When we have a purely resistive circuit, the current follows the voltage. So there is no phase, angle, or delay between the current and the voltage. Because capacitors store voltage, there's already voltage out in the circuit. And because of this, the current leads the voltage by 90 degrees. When we have an inductive circuit, the inductor chokes back the current, and we say that the current lags the applied voltage by 90 degrees. When you compare the capacitive current to the inductive current, you will notice that they, with respect to each other, are 180 degrees out of phase. Resistance is the opposition due to the material. When we have an inductor or a coil, we have inductive reactance, which is the opposition due to the magnetic properties of the coil. A capacitor stores voltage, so we end up with a capacitive reactance that turns out to hold back current due to an opposition due to changing voltage. In the previous slide, we looked at our current relationships for these three. Our resistive current was in phase. There was no lag. So our resistance in ohms also turns out to be 0 degrees. Our inductive current was lagging by 90 degrees. And that results in our inductive reactance being at plus 90 degrees. Finally, our capacitive reactance derives out to be minus 90 degrees because the current leads by 90 degrees in a purely capacitive circuit. We have to keep these vectors in mind when we're combining them in a circuit. When you compare your inductive reactance to our capacitive reactance, or any of our reactive values, you will notice that your inductive values are 180 degrees out of phase with your capacitive values. And this makes the math a whole lot simpler. So what about when we have a series RLC circuit? Well, as our current flows through the circuit, both the resistance, the inductive reactance, and the capacitance are going to impact the current. Again, series oppositions add, but our resistance is at 0 degrees, our inductive reactance is at plus 90 degrees, and our capacitive reactance is at minus 90 degrees. So that our overall opposition is a vector sum of those things. Now if we're using Pythagorean's theorem in order to solve a triangle, it would be z squared is equal to r squared plus whatever the resultant is of our reactive side squared. So you have to take the difference of these two over here and then square it. So now we have z squared is equal to r squared plus xt squared. Now depending on the values of our capacitance and our inductance, if our circuit works out to be more inductive, then our z will have a positive angle. But if our circuit turns out to be more capacitive, well, then we'll have a negative angle on our z impedance. The angles are impacted by whether we have more inductance or more capacitive impacting the circuit. Our total impedance Z is equal to R plus JXL. Again, the plus J being plus 90 degrees minus JXC. Again, our J operator indicating that XC is at minus 90 degrees. The J's, we get the difference between those and we add them into our R, and we can end up with our polar form, which is our magnitude with a direction for our total impedance. So let's take a look at an example with some numbers, shall we? Here we have a simple circuit. We have a voltage of 280.5 volts at 60 Hertz. And then we have an RLC series not a combination, just a series circuit. We have a resistance of 30 ohms at 0 degrees. We have an inductive reactance of 54 ohms at plus 90 degrees. And then we have a capacitive reactance of 35 ohms at minus 90 degrees. When we go to vector sum these values, we have to take the difference between the capacitive reactance and the inductive reactance, which in this case works out to be 16 ohms. Now that we have that difference, we can find our resultant triangle, or magnitude with direction, or vector sum, if you wish. If you have that function on your calculator, you can simply put it in as it is, or if you need to use Pythagorean's theorem, you can do that as well. Now keep in mind, the angle of our Z impedance is a function of the reactance total, or difference, with respect to our resistance. In this example, it works out to be 34 ohms at an angle of 28.07 degrees. That's because we have more inductive reactance impacting our circuit than capacitive reactance. Now that we've calculated our total impedance to be 34 ohms and 28.07 degrees, we can calculate our current, which works out to be 8.25 amps at a lagging 28 degrees. Again, our inductance has more influence on the circuit than our capacitance, so our current will be lagging, and in this case by minus 28 degrees. Once you have your current, you can calculate your voltages, where the voltage across the resistor will be 247.5 volts, the voltage across the inductor 420 3/4, and the voltage across the capacitor 288 3/4 volts. Kirchhoff's voltage law says that sum of voltages have to add. So when we vector sum these voltages, you have to bear in mind that your capacitive voltage and your inductive voltage are 180 degrees out of phase. So when you vector sum them, you have to take the difference, which in this case works out to be 132 volts. When you take that resultant voltage and add it to your resistive voltage, you do indeed get back to your total source voltage of 280.5 volts. So now in a series circuit, we've looked at our overall impedance, we've looked at our voltages, that just leaves powers. Again, when we had a resistive circuit, our true power in watts was when the resistor converted electrical energy into heat energy, and we use P to represent that. Our capacitor stored energy in an electrostatic field, and we used QC as the identity, and we measured that in VARs capacitive, volt amps reactive. And our inductor stored electrical energy in a magnetic field. We used QL as the identity, and we also measured that in volt amps reactive. Let's finally look at all three currents and powers together. When we apply a voltage, our resistive current will be in phase with our voltage, as we had seen earlier in this presentation. I've left that out just because it gets very busy, as you will see in a moment. Because of the nature of our inductance, it holds back the current or chokes the current. And it turns out the inductive current lags the voltage by 90 degrees. So as you can see here, when my voltage is at 90 degrees, my current is only starting to go up in my inductor. So there's a 90-degree lag between when the voltage starts to go up and when my inductive current starts to go up. That's what we mean by a 90-degree lag. Because our capacitor stores voltage, it supplies current immediately. So you will see here that our capacitive current is actually leading or ahead by 90 degrees. So there's a 90-degree difference in my capacitor and my voltage, but this time the capacitor is ahead of the voltage by 90 degrees. Now when we start looking at our powers, when we multiply our inductive current by the voltage, you can see that in this particular quarter here, my voltage is positive and my inductive current is positive, which results in my inductive power being positive. In this first quarter here, my voltage is positive, but my inductive current is negative. That results in my inductive power. Well, it appears to be negative, but can you really have a negative power? What would a negative power be? Well, that's when my inductor is actually collapsing its magnetic field. So that during this whole section here, my inductor is actually giving me back the energy it had stored. And during this positive pulse in here, my inductor is actually storing energy or building up energy. You will notice that my inductive power now is twice the frequency of my voltage frequency. And my inductor is constantly playing this game of discharging and charging, discharging and charging. So it's giving me energy back, and then it's storing energy. It's giving me energy back, and it's storing energy. Now when we multiply through and take a look at our capacitive reactive power, and this is what I was saying about it gets a little busy. As our voltage is going up, our current is positive. So here in the first quarter, my capacitive reactive power is positive. That means we're storing energy in our capacitive static field. During the second quarter in here, our capacitive current is negative, but our voltage is still positive. So in this case, my capacitor is giving me energy back. Now, if we compare just our powers, our capacitive reactive power and our inductive power, you'll see that when my inductor is discharging, my capacitor is charging, and vice versa. When my inductor is charging, my capacitor is discharging. My two reactive powers are 180 degrees out of phase. And this is a really wonderful thing, because when my capacitor wants energy, my inductor doesn't want energy. And so we can use our inductive energy to supply our capacitive circuit. And when my inductor wants energy, my capacitor doesn't want energy. And so my capacitive component will actually feed my inductive component. Now, depending on whether it's a series or a parallel or a combination circuit, this will dramatically impact my currents. And we can actually get a little something for nothing. Let's continue to take a look at that, shall we? So here we have the circuit we were working on earlier. We calculated out the total impedance to be 34 ohms, our current to be 8.25 amps, and then we calculated out our individual voltages. And it's because of this feeding relationship, where our capacitor can feed the inductor and the inductor can feed the capacitor, that we can actually end up with voltages that are much higher than our source. And that's what I mean about getting a little something for nothing. It's also part of the reason why, as electricians, we don't really do series RLC circuits, because our overall voltages can be a lot higher than what we can expect. This type of circuit does come in very handy when we want to do voltage multipliers. But let's carry on and continue looking at our power relationship, shall we? Now that we have our total impedance, our total current, and all our individual voltages, we can calculate out our individual powers. Now remember, if we want our total power, we have to do a vector sum of our individual powers, where QC and QL are 180 degrees out of phase. So we have to take the difference of those two, which in this case leaves us with a result of 1,089 VARs that are net inductive. We can now vector sum our resistive true power with our net reactive power, and then we can get our total apparent power. As before with series circuits, we could use ETIT to calculate ST, and now we can calculate our power factors. Because we have a net inductive power left over, our power factor will be a lagging power factor. In this case, 88.23%. Again, good practice. Go back and double check your angle by taking the arc cos of the power factor, and sure enough, we get back to our 28 degrees. Let's see how it works in a parallel RLC circuit. All of our tenets for parallel circuits still hold true. Voltage is common. The current is the sum of the individual branch currents. Kirchhoff's current law says the sum of currents entering the node must equal the currents leaving the node. This one can be a bit misleading with RLC circuits, because our capacitive reactance and our inductive reactance cancel each other out. So when you're comparing this, you have to look at the vector sums. But it too still holds true. When looking at the impedance, it is again a reciprocal sum that adds vectorially. But as always, power always adds. That relationship is going to play a bigger role in the next few minutes. So when we have a parallel circuit, our impedances are a vector sum, but it's a reciprocal in vector sum. So that 1 over ZT is equal to 1 over R plus J1 over XL minus J1 over XC. This function can be performed on your calculator if you have a rectangular to polar function. But if you're doing Pythagorean's theorem, you have to take the reciprocal difference of your reactive pieces first before you square them. Because again, Pythagorean's theorem only works in a triangle. So too, when you're taking the angle, you have to take the reactive reciprocal difference and then divide by the reciprocal of the resistance. If you perform this mathematical operation correctly, you should end up with 20 ohms at minus 36.87 degrees. It may take a bit of practice to get used to that, and it can be a challenge. Now that we got total impedance, we can get our total current, which in this case works out to be 5 amps at plus 36.87 degrees. That's because our capacitance allows more current to get through than our inductance. So our capacitance actually has a larger influence in this example. The reciprocal sums can be a bit of a challenge. But in a parallel circuit, currents add nicely. So let's take a look at it from adding a current perspective, shall we? In our previous slide, we calculated out the impedance using an impedance triangle. Since impedances are a reciprocal vector sum, it can be a bit of a challenge. Not impossible, just challenging. And we ended up with 20 ohms and 5 amps. But when we reflect back on our parallel tenets, current adds nicely. It's still a vector sum, but we don't have to worry about all the reciprocals. So let's use current to calculate out our Z impedance. Since voltage is common, it's easy to find our individual branch currents, where our resistive current works out to be 4 amps, our inductive current 2 amps at minus 90 degrees, and our capacitive current works out to be 5 amps at plus 90 degrees. Again, our reactive sides, we have to take the differences, because our plus 5 amps is at 180 degrees to our minus 2 amps. So we need to take the difference of those two to get a resultant in order to build a triangle. That leaves us with a net current of 3 amps capacitive, or plus 90 degrees. We can now vector sum our 3 and 4 amps, and sure enough, we get to our 5 amps. Now that we've calculated all our individual branch currents, we can go on to calculate all our individual powers, where our total apparent power, ETIT, will give us 500 VAs. Now, as we stated earlier in our tenets, our individual powers should add up to our total power. When we calculate out our resistive power, we get 400 watts, our inductive reactive power, 200 bars, and our capacitive reactive power, 500 bars. And this is part of the interesting thing about RLC circuits. You may notice that our capacitive power is the same as our total power, but our resistor also has 400 watts and our inductor also has 200 bars. Again, that goes back to the fact that the capacitor and the inductor will feed each other. When the inductor is discharging, it's going to supply its 200 bars worth of energy to our capacitor, which means our capacitor really only needs 300 bars worth of energy to be supplied from the source. So when we vector sum our powers, our total apparent power, 500 VAs, is equal to our 400 watts on our resistive side and the difference in our reactive powers of 300 bars for our capacitor. And sure enough, when we add these two vectorially, we get back to our 500 VAs. When we calculate our power factor, we end up with an 80% leading power factor. We say it's leading because our circuit is more capacitive than inductive. Our current, our 5 amps, is at a leading 36.87 degrees. So we say that our power factor is leading in a net capacitive circuit. Whereas before we had lagging power factors when it's net inductive. Again, we can use our power factor to go back and double check and verify our angle. And sure enough, we get back to our 36.87 degrees. Let's take a look at our combination circuits. An RL combo by itself, as in this particular diagram, is probably one of the most common circuits in electrical. Because any sort of inductive circuit, whether that's a motor or a transformer, has both resistance and inductance. So it works out to be an RL series combination. We don't usually put capacitors in series because that causes our current to go up, which, in result, causes our total apparent power to go up and can cause some high voltage spikes. If that was a motor circuit and our motor was then getting more voltage than it originally wanted, it may react differently. It may spin faster, or it may burn up. So it's not practical to put capacitors in series with motors. So we often place capacitors in parallel with motors. And that's what makes this series parallel combination one of the most common circuits for electrical electromechanicals. So how would we go about solving something like this? Well, when we compare and contrast our series and parallel tenets, we need to look for something common. In series, voltage adds, current is common, resistance adds, well, vectorially, and power is always add. In parallel, voltage is common, but current adds. And resistance is a reciprocal sum. But powers also add directly or vectorially. It doesn't matter whether it's series or parallel. Powers always add. And that's the big secret to solving any AC combination circuit, is you need to use powers to solve the circuit. This saves on a lot of complex math where you have to take all of your vectors, break them down into their x and y components, or their rectangular form, in order to vector sum the totals. If you calculate out your individual powers, they are already in their rectangular forms. They're in the most basic x and y components. So all I have to do is put them together to create one resultant triangle. So what does that look like? Let's take a look. Here we have a simple RLC combination circuit, where our resistance and our inductance are in series, just as it would be in such thing as a motor or a transformer or a coil. We've placed our capacitor in parallel with these two. That way our RL combo gets the voltage that it wants or requires. In this case, 340 volts. Now you'll notice that L and C this time I've given you in their millihenries and their microfarads. So we'll have to convert those over into ohms along the way. Since the RL combo gets the full 340 volts and our capacitor by itself gets the 340 volts, we can examine those as if they were individual circuits. Again, we're going to use powers to solve our total current and our total impedance. So let's isolate our RL combo first. When we convert our inductance to inductive reactance, we end up with 8 ohms in series with 15 ohms inductive. Those two together will result in 17 ohms impedance at an angle of 61.93 degrees. That 17 ohms will give us 20 amps in that first branch. That 20 amps will then give us a power of 3.2 kilowatts in the resistive piece and 6,000 bars in our inductive piece. Now when we isolate our capacitor by itself, we end up with 3,600 bars capacitive. I use the E squared over ohms formula in order to get to my power directly. It's quick and easy. Now that we have our 3 individual powers, we can go on to build a power triangle, because powers always add. I'm sure you'll agree with me that this particular exercise in finding the powers is actually pretty easy. So here's our 3 powers that we calculated in the previous slide. We can now build a power triangle where our true power in watts is on our 0 axes. And that's 3,200 watts. Our net reactive power is the difference between our inductive power and our capacitive power. And that results in 2,400 bars inductive. We can now add our 3,200 to our 2,400, and that gives us 4,000 VAs of total power. That results in an 80% lagging power factor. Again, because our circuit is net inductive, which will result in a lagging current, which then results in a lagging power factor. Using our power factor, we can now calculate the angle for the circuit. So our total circuit values will all be at 36.87 degrees. Since it's a lagging power factor, that means our current will be lagging by 36.87 degrees. With our total apparent power, we can now calculate our total current that we drawn from our supply, which in this case turns out to be 11.76 amps. The capacitive current will help feed part of the inductive circuit, so that the 20 amps in our RL circuit, part of that 20 amps comes from the 11.76 of the total circuit and whatever the current is in the capacitor. And again, that's part of the beauty of an RLC circuit, is that my capacitor will feed the inductor, and the inductor will then dump into the capacitor, which means my overall current will actually go down compared to my branch current of my RL circuit. Once we have our total circuit current, we can get our total circuit impedance using ET over IT. In this case, it results in 28.9 ohms. When it comes to combination circuits, it's almost like we're working backwards from a series circuit. In a series circuit, we found our impedance, we use that to find our current, and then we used our current to find our powers. In a combination circuit, we started off by finding all our powers. Then once we found all our powers, we were able to find our total power, and from our total power we got our total current. Then once we had our total current, we were able to find our total circuit impedance. So it's sort of like working backwards. Now that we've looked at our series, parallel, and combination circuits, let's do 3 practice problems, one of each. Now, if you recall before we get started, the easiest way to solve a series circuit is to build an impedance triangle. The easiest way to solve a parallel circuit is to build a current triangle. Finally, the easiest way to find or solve a combination circuit is to build a power triangle. So for our first practice problem, let's do a parallel circuit. Now remember, in a parallel circuit, the easiest way to solve it is to build a current triangle. Currents add nicely in parallel. If you want to work on this problem on your own, I encourage you to pause the video now. And then you can follow along with my solution after you're done. So if you're going to pause, do it now. So let's carry on with the solution, shall we? When we go through and calculate out all our individual branch currents, we end up with 48 amps resistive, 24 amps inductive, and 10 amps capacitive. When you take the difference between the capacitive and the inductive circuit, you end up with a net 14 amps inductive. When you vector sum your resistive current and your net inductive current, the result is 50 amps, 50 amps, at a lagging 16.26 degrees. Once we have our IT, it's very easy to calculate our ZT, which in this case works out to be 9.6 ohms at 16.26 degrees. Again, you can do the reciprocal sum if you wish, but don't forget, it's a reciprocal vector sum. It's just easier to take ZT as ET over IT. Now that we have all our currents, we can calculate out all our powers. Our total apparent power is 24 kVAs. True power, 23.04 kilowatts. Our inductive power, 11.52 kVARs. And our capacitive power is 4.8 kVARs. Again, we should double check and vector sum our powers together to see if we get back to our total apparent power, where our net reactive power is 6,720 VARs when we take the difference between our inductive power and our capacitive power. And sure enough, when we add that together with our true power, we get back to our 24 kVAs. With our resistive power and our apparent power, we get a 96% lagging power factor. And when we verify our power factor with our angle, sure enough, we get back to 16.26 degrees. So I hope you got along with that well enough. So for our next example, let's do a series circuit, shall we? We got a source of 455 volts at 60 Hertz, an RLC circuit with 63, 44, and 60 ohms respectively. If you want to solve this on your own, I encourage you to pause the video and work your way through. Then again, you can verify your answers to my solution. I want you to find all the values, your total impedance, your total current, all your voltages, and all your powers. It's a series circuit, so we're going to be building an impedance triangle. So if you're going to pause the video, pause it now. With our individual ohms, when we vector sum them together, we end up with a result of 65 ohms at minus 14.25 degrees. Our capacitance has more influence than our inductance, so we have a net capacitive circuit. Because it's a net capacitive circuit, that means we'll end up with a current of 7 amps at a leading 14.25 degrees. Now that we have our current, we can calculate our individual voltages, where we end up with 441, 308, and 420 volts respectively. With ETIT, we can get our total apparent power, ST, and we can calculate out our individual powers. With our individual powers, we can double check our total apparent power by vector summing them, and sure enough, we get back to our 3185 VAs. With the total power and our resistive power in hand, we can now calculate out our power factor, which in this case is a 96.92% leading power factor. Again, it's leading because it's a net capacitive circuit. Hi, buddy. Once we double check our power factor, we can use it to calculate out our angle and compare that to our original calculation. And sure enough, we get back to our 14.25 degrees. Finally, let's do a combination circuit. Now remember, in a combination circuit, we're going to break it down into 3 parts. We're going to find the individual powers by dealing with each branch individually. Then, once we have all the powers, we'll put all the powers together to build a power triangle. Once we have our total power, we'll use it to find our total current, and then finally our total impedance and our angle. So if you want to work on this problem on your own and compare your answer to mine, pause the video now. So starting off this problem, we'll do the first branch with our RL combo. That results in 240 ohms total impedance for that branch, 2.5 amps in that branch, which gives us 1.2 kilowatts and 900 VARs inductive reactive power. Next, when we isolate our capacitive branch, we get 400 VARs capacitive reactive power. With all our powers in hand, we can get our total apparent power, which in this case works out to be 1300 VAs of total apparent power. That then results in a 92.3% lagging power factor. Taking our power factor in hand, we can then calculate the total circuit angle, which in this case works out to be 22.61 degrees. With our ST and our ET, we can get our total current, which in this case works out to 2.166 amps repeating. Again, this is less than our inductive branch current. That's because our capacitor is feeding some current into it. With our total current, we can calculate our total circuit impedance, which in this case works out to be 276.9-ish ohms at 22.61 degrees. Because we have a more influential inductance in our circuit, our current is lagging, which means that our power factor is lagging. So what did we get out of this presentation? Well, when we're solving a simple series RLC circuit, the easiest way to the solution is through an impedance triangle. When we're dealing with a parallel circuit, it's the easiest to start off by building a current triangle. Finally, when trying to find a solution of a combination circuit, the easiest way to do it is to isolate each of the branches. Solve those branches to find the individual powers. Then build a power triangle with all the individual powers. Use your total power to find your total current, and use that to find your total impedance. With your total powers, you can also find the circuit angles. This concludes our presentation on combination RLC circuits. Thanks for watching. Until next time.